Hi, a beautiful day to everyone. Welcome back to our General Mathematics class, lecture series number 4. Our focus today is the rational function. But before we're going to look into the rational function, now may I show to you first the platform or online platform that I'm using in my class. So I'm using YouTube channel. So I have in here the channel Agipad, and I'm using the uh, Facebook, which I always make an announcement. So these are the two platforms that I'm using. So when you will be watching the videos or a series of lecture that I'm having, please look into my name Agipad as my account in the YouTube, and look for the different topics that you will be needing in your lesson. Once again, before you're going to watch the video, may I encourage you to please subscribe and click the notification bell so that if I have new lesson, you will always be reminded. Okay, so let's start with our new lesson today. So, the rational function. So, you will notice in here, the rational function has so many use in the daily life or in the business world. So one of the use is we have in here. It is used to compute the average speed over a distance traveled by a certain locomotor, or shall we say vehicle. Another one would be the concentration of mixture that is used in the chemistry. The next one would be the average sales over the time. Okay, so more specifically in business, and the average cost over the time. Okay, so these are only few use of the rational functions. So to start with, we need to go over with certain concept. So before we're going to have the rational function, there are prerequisites that you need to understand. Now, what is this? The concept that you should understand is what is a rational number. So when we say rational number, it is a number that can be expressed in a fraction. Example is that we have in here 5 over 2, 3, or 4.5. Is 3 a fraction? Yes, that is the same as a fraction. Now what would be its denominator? The denominator of 3 is always 1, or the denominator of a whole number is always 1. Now what about the decimal point or decimal number 4.5? Yes, that is still considered to be a fraction when we convert them into a ratio form, which is the same as 4 and 1 half. Another thing that you need to understand is the number irrational number. Now, what do we mean when we say irrational number? When we say irrational number, these are numbers that cannot be written in fraction. Say, for example, we have in here pi, or the square root of 2. This number cannot be written in fraction form. So, those are the things that you need to understand. Another one would be the rational function has form. Now, what is the form of a rational function? The form is always written in the form of f of x is equal to p of x over q of x. Now, p in here and q in here are considered to be a polynomial. Okay. what is meant by rational equation. Now, when we say rational expression, it is an equation containing rational expression. This expression in here could be any algebraic expression. So, any kind of polynomial. But it is not necessary that those polynomial or algebraic expression are said to be a function. Another one in here is a rational expression is an expression of the form y is equal to p over q, wherein p and q are non-zero polynomials. So they are non-zero polynomials. Now you will notice the forms. I equated y with the given ratio of p over q. So unlike in the rational function, you will notice the difference. The rational function is written as the quotient of two polynomial functions. So here is the form. R of x is equated to or is equal to p of x over the q of x, where p of x and q of x are both polynomials. It says even in here that q of x should not be equal to 0. And the domain of the rational function r of x are all real numbers except the numbers that will make the q of x 0, or the number that will make the q of x 0 is not included as the domain of the rational functions. Now let's try to see some application of rational functions. It says in here in the number 1 statement, represent the speed of a taxi as a function of the time it takes to run 1,000 meters in the highway. Now you will notice the representation is 1,000 meters over x. You'll notice that it is similar to the formula for the speed, wherein speed or s is equal to d over t, which is d is the distance, t is the time. Another one in here is if it takes 3 hours to drive a distance of 192 kilometers on a motorway, what would be your average speed in kilometers per hour? So again, speed is equal to distance over time. And so how are we going to compute for the average speed? The average speed is equal to the quotient of 192 kilometers divided by 3 hours. So it will give you an average speed of 64 kilometers per hour. How is that? That is the same as 192 divided by 3. It will give you 64. And so the answer would be 64 kilometers per hour. How are we going to graph rational function? When we are going to graph rational function, we will understand this one when we are going to consider example of a rational function. We have in here an example of rational function, which is the very basic rational function. F of x is equal to 1 over x. So that when we are going to graph this one, you will notice that there are steps or suggested steps that you must be doing. One in here is determine the domain of the rational function. Again, when we are going to have the domain of the rational function, we have to consider the restriction. The restriction is that the denominator must not be 0. Number 2, after determining the domain of the rational function, Now we're going to state some values of x. So after having now the different values of x, that's the time we're going to evaluate the function. And after evaluating the function, we're going to place them in a table and plot them. We're going to draw and plot the function. After plotting the function, we will label the graph of the function. Let's start. So what is the solution of the f of x is equal to 1 over x? Of course, we have to determine the domain so that the domain of that function are all real number except 0. Why except 0? Because the limitation is that denominator must not be 0. After having now the domain, that's the time we're going to state the possible x that we will be considering in evaluating the function. So x are all real number except 0. So I have in here the table. I will assume possible values of x. So you will notice in here, my possible values of x would be from negative 1 to infinity and from positive 1 to infinity. Or shall I just consider this one, negative 1, negative 2, negative 3, negative 4, and positive 1, positive 2, positive 3, positive 4. Now you will notice in here between negative 1 and positive 1, I did not consider 0. Why did I not consider 0? Because we have said that 0 should not be considered to be the value of x because of the restriction of the rational number. So let's compute, let's evaluate or solve the value of the function. If my x is equal to negative 4, so I have in here the computation. F of x is equal to 1 over x, the original function. What if my x is equal to negative 4? So I am going to evaluate. I am going to say f of negative 4 is equated to 1 over x, which is negative 4. After having this one, I will be dividing. 1 divided by negative 4 will give you negative 0.25. So the value of my function, if my x is negative 4, is negative 0.25. So that is how to evaluate. So this method of evaluation will be true to all values of x. Let's consider continuing the evaluation of some values of x. So you will notice that if I have negative 4 again, it will give me a result of negative 0.25. What about if my x is negative 3? What would be the value of f of x? It will give me a result of negative 0.33. What about if my x is negative 2? What would be the value of f of x or y? It will give me a result of negative 0.50. What about if my x is negative 1? The value of f of y will be negative 1.0. Continuing the evaluation, I have in here now the possible values of f of x. So after having now the values of f of x or y, or shall we say the range, I am ready now to draw and plot the function. Of course, I'm going to consider the different coordinates. So I have at least 8 coordinates. After having these coordinates, I'm going to draw my Cartesian plane. And having the Cartesian plane, I'm going to plot the different coordinates. Now you will notice in here I have two graphs. Why two graphs? because as you can see, the computation or the possible value of the domains are divided into two groups, divided by the uh, value of x, which is not considered to be the domain, that is 0. So I have the negative, I have the positive x. So you will notice in here, if I have negative 4, it will give me a y which is negative 0.25. So I have in here the negative 4. Now it is located, this negative 4, this point is located in here, at least that is negative 0.50 25. What about if I have negative 3? Of course, you will notice in here the negative 3 is located in the third quarter. You will notice that this one is with a corresponding value of y, which is negative 0.33, at least in here. Now what about if I have negative 2? You will notice my negative 2 is uh, within this point. Now this point corresponds to negative zero point 0.5 or negative 0.50. And another one in here is if I have negative 1, it will give me negative 1 as my y. So this is my negative 1 as my x, and this is my negative 1 as my y. Now I did not connect this one because, as I said, it was broken, caused by the denominator. What about if my x is positive 1? Of course, the value of my y is positive 1 also. Now, where is this coordinate? It is located in here. So you will notice that this point correspond to my positive 1 as the value of my x, and this point correspond to the value of my y as positive 1. Now you will notice in here that if I have x to be positive 2, my y would be zero point 0.5. So here is my positive 2. So it is in here, the point is in here. This point corresponds to my y, which is positive 0.5 or 0.50. Now what about if I have my x to be positive 4? My y would be 0.25. So here is my positive 4. So the point is located in here, and it will give me at least, or it corresponds to 0.25 as my y. So that is how to graph uh, the function, the basic function f of x is equal to 1 over x. After having now the graph, I'm going to label them. So within here, the title of the graph. So this is my y. Okay. So here, this is my y, the vertical line. And my domain input or x is the values of my x. It is at the bottom part. Now what about if we are going to consider a more complicated rational function as compared to what we just had computed a while back? So we have in here a rational function f of x is equal to x plus 3 over x raised to 2 minus 9. Again, to have the computation of this problem and a graph of this problem, there are suggested steps that we're going to make use. So we have in here, determine the domain of the function, assume or state the values of x, evaluate or solve the function if we have already stated the values of x. After having the evaluation, draw and plot the function, and of course label the graph of the function. Here is the solution of the rational function that we have. The domain of the rational function are all real number except -3 and +3. The question is why? It is because when you evaluate the denominator using -3 or +3, the value of x will make the denominator 0. Let's consider this computation. So we have in here f of x is equated to x plus 3 over x raised to 2 minus 9. That is the original function. Now considering that we are saying that -3 and +3 are not supposed to be included as the domain of the function. Using -3 as the value of x, we will check if it will give a result of 0 in our denominator. So you will notice the quantity -3 raised to the second power minus 9 is equal to 0. The quantity -3 raised to the second power will give you a result of 9. So 9 minus 9 will give you 0. And so you will notice when this will be our denominator, there is no rational function to speak. Why? Because the numbers we're talking is considered to be undefined number. So that is just to say that the domain of the rational functions are all real number except -3 and +3. So the domain of the rational functions we have is that x are all real number except -3 and +3. So after having now the restriction of the rational number, we can now assume the possible values of x. So I have in here from -6 to +6. You will notice I did not include -3 and +3. Why? They are the restriction of the rational number or rational function. So what about if we are going to evaluate if our x is -6? I have in here the computation. So you will notice my computation in here, f of -6 will give you this statement -6 plus 3 divided by the quantity -6 raised to the second power minus 9. What did I do? I replace the x with its value -6. So you can see -6, -6. Now after having the replacement or substitutions of the x in the numerator and the denominator, do the indicated operation. So I have in here the indicated operation in the numerator. -6 plus 3 will give you -3. The quantity -6 raised to the second power will give you 36 minus 9. And so 36 minus 9, it will give you 27. So I have in here 3 divided by 27 will give you negative 0.11, which is this one. So that is how to evaluate the function using the given values of x. Now what about the value of my f of x or y if my x is negative 5? Now follow the same pattern in here. Replace the value of x, and after that one, do the indicated operation. Let's continue. Now I have in here the table. You will notice that if I have negative 5, the value of my y would be negative 0.13. If I have negative 4, the value of my y would be negative 14. If I have negative 2, the value of my y or f of x would be negative 20. If I have negative 1, my y would be negative 0.25, and so on and so forth. And if I have the value of my x to be 6, the value of my y would be 0.33. So those are the evaluated values of the function. So after having now the evaluation of the function, we are now ready to plot the graph of the function. Of course, when we are going to plot the function, we have to collect the different coordinates from our evaluation. Okay, so I have in here the table of my coordinates. Having gathered the coordinates, that's the time I'm going to draw my graph. Okay, so I will draw the Cartesian plane. After having now the Cartesian plane, I will plot the points. So I have in here the graph. Okay, so the blue one. So from negative 6 going down or going up to positive 2, the graph is from the uh, third Cartesian plane, okay, going down in here. Okay, now you will notice this graph will not touch this broken line. I will soon discuss why. Okay, but to have at least an idea, this graph is asymptotic to this line, vertical line. Now you will notice also that when my x will be from from positive 4 going up to positive 6 or to infinity, now you will notice that my graph will be coming from this point, going down, and it will be going to your right. So again, you will notice the purpose of this arrow will tell you the direction of the graph. Okay, so it will go up, it will go to the right side, this one will continue going to the left side, this one will continue going to the below the graph. Okay, now you will notice also that the arrows in here we have in here will not touch this broken line, the red broken line and the blue broken line. Why? Because this graph are asymptotic to this vertical line and to the horizontal line. Okay, soon we will explain to you the meaning of horizontal and vertical asymptote. Now after having the graph, that's the time we're going to label. After plotting the graph, now you will notice that I have broken line in here and in here. The horizontal the horizontal blue broken line and the vertical red broken line. Now, you will also notice in here that I have a hole in here. Now, what are these? So, the blue broken line is called to be the horizontal asymptote. And the hole in here, which will probably disconnect the graph, is named as removable discontinuity. Another one in here is the broken red vertical line. What is that? It is called to be the vertical asymptote. The horizontal asymptote, the vertical asymptote, and the removable discontinuity will be expound more on our next series of discussion. So I hope as we go deeply in studying the general mathematics, you still have the time to smile because we cannot do otherwise. But we need to understand this lesson. Okay. So as I said, smile. Okay. So in the next lecture series, we will be discussing a very interesting topic, the concept of asymptote. Okay, the concept of asymptote. Before we end this lecture, I hope I shared to you ideas about rational function in my humble capacity. And please click subscribe button and click the notification bell so that you will be reminded of the new lesson posted. And thank you for lending me your ears.